Hello, Algebra 2 students. I appreciate you finding time to get your notes taken care of. Today we're going to be looking a little bit deeper into the rational functions by taking a closer look at the equations that accompany them. Please copy down your title, Equations of Rational Functions, and your objective, which is the student will learn to interpret the equations of rational functions. As always, press pause anytime you need more time to get something copied down, and then hit play when you're ready to move on. So let's take a look. Now, as you undoubtedly know, in recent weeks we have learned how changing various values in a function can affect the graph of that function. Now, that's kind of an obvious statement because obviously changing an equation definitely changes the graph and vice versa. Today we're going to be seeing that many of the same adjustments that we learned to make with quadratics, the parabolas, and also the square root functions also hold true for the rational functions. So all this stuff has been a little bit complicated for us to get our minds wrapped around. It is the same complication as we move from type of graph to type of graph. So hopefully it's getting sunken in. Okay, now as we saw yesterday, the parent function is y equals the reciprocal of x. And of course the inverse would be x equals the reciprocal of y. Now this parent function can be adjusted in many of the same ways that the other functions we've been working with can be adjusted. So the general form, okay, or the standard form of our square root function is going to read y equals. Now, it's not always a 1 that's in the numerator of a rational function. So it could be any constant that's up there. In the denominator, we still have, in this case, x, since the y is isolated. X can have an adjustment made to it by way of minus h, also in the denominator. And then, of course, y can have an adjustment made to it by a constant being added or subtracted to the end, so we have plus k. Okay, so let's define some of this information. Make sure we understand exactly how to read it now that it's in a different type of function. Now, this is a hyperbola. Type of graph is a hyperbola. We discussed that yesterday. Now, a hyperbola does not particularly have a vertex at the central location of the hyperbola. It has what's called a center. Now, technically, the hyperbola does have two vertices, but they are located on the curves themselves. We'll get to that a little later. Okay, so for right now, just understand that h comma k is the center of the hyperbola, and it will occur in the space between the two curves of the hyperbola. Just as before, the sign in the denominator, in this case that is in between x and h, the sign in the denominator is built into the formula. So that negative is supposed to be there. And if it is not, then the only possible explanation would be that the constant that follows that sign must have had its own negative and changed it to a plus. The asymptotes for the hyperbola, we discussed last time that there are two asymptotes in a hyperbola, and as the center of the hyperbola moves, the asymptotes will move along with it. So do not fall into the trap of thinking the asymptotes are always at x equals 0 and y equals 0. They're not always on the axes. They were on the axes before because the parent function had its center at the origin. Okay, some more adjustments. Now the value of a in the numerator there changes the speed of the graph. Okay. Now as a could be a larger number than 1, like a 2 or a 3 or a 4 or so on, okay, then that would obviously change the speed. But also keep in mind a might be a fraction, which typically we do not put a fraction in a fraction. That's called a complex fraction. We don't typically do that. So you will also watch out for possible constant changes down in the denominator. Okay, if you see some constant changes in the denominator, then you need to interpret that as a is a fraction and that information spilled into the denominator as a result of that fraction. Okay, now same thing as we have seen in the past. If a is a value smaller than 1, now that would be the instance that I was just discussing, that it's trying to be a fraction smaller than 1. If that's the case, then some of a's information might be in the denominator, and that is going to cause the parabola to pull in closer to its center. Okay, so basically what we're saying here is if a is smaller than 1, if the coefficient is a value smaller than 1, that is going to draw it further or closer into its center, and it's going to take longer to move to infinity. Now, of course, a equaling 1 is the normal speed that matches the parent function. And the last option would be the constant a is larger than 1. That's going to push it further from its center, which pushes it closer to infinity. Now, as far as sign changes are concerned, okay, this should feel very much the same as the skills that we've already learned. Reversing the sign of the a, which is basically reversing the sign of the entire fraction that is up there. Okay, that will reverse the direction of the isolated variable. So in this case, if a has a sign change, or if the fraction has a sign change, then that is going to reverse the direction of the y-axis. Reversing the sign of the denominator, on the other hand, okay, would reverse the direction of the axis in the denominator. Okay, so if there is specifically a sign change going on in the denominator, then that is going to send that axis the opposite direction. In this case, it would be the x-axis would be reversed. Now, we spent a little bit of time last unit making sure that we were interpreting the axes correctly. Okay, so that skill is going to remain in effect here. So remember that reversing that variable, okay, the one in the denominator in this case, also reverses the sign of the center when you are identifying that coordinate. Okay, so remember, you've got that extra little sign change with the variable that is attached, okay, or the part of the center that is attached to the variable in the denominator. So in this case, h would experience an extra sign change if the x-axis was reversed. Okay, so let's take a look at how some of this stuff works. Okay, we're going to begin again with the parent function. The key to getting the graphs correct is to really understand what the parent function is supposed to be doing. If you can get that, then all you have to do is ask yourself how the graphs have changed. Okay, so we're going to get a graph of the reciprocal of x, okay, the parent function for the rational functions. Okay, now we have already experimented with these values, so I'm not going to trouble you to go through all of these values again. Okay, if we pick several values moving away from the origin on the x-axis, now of course we pick some fractions very close to the center because the graph is changing radically in that area. Getting just 1 or 2 points is not going to be good enough for us to see how the graph is actually curving. So I actually pick 1/4 steps moving away from the center point until I get about a unit away, and then I start taking whole steps. Okay, but anyway, plugging these values into the reciprocal function up there, okay, we end up with a whole bunch of ordered pairs. So of course there they go, and you connect the dots and you have half of your hyperbola. Okay, repeating the same process for the opposite side of the center point, we end up with these values, and once again we are selecting some test points, again very close to the center point. I'm only moving in quarter steps because I'm concerned about how fast that graph is curving, but as I get about a unit away from the center point, then I start moving in whole steps. But plugging these values into the reciprocal function, we end up with these ordered pairs. When we plug in our points, we end up with those plots. And when we connect the dots, we have our parent rational function. Okay? This is what your assignment yesterday was involved, was generating this graph. Okay? Now, if that's the parent function, then let's take a look at some that are not the parent function. Clearly, this equation is not going to give the parent function because we have adjustments that are being made to it. Now, hopefully you can look right at this equation and almost instantly recognize that nothing has been changed except for the position of the center. Okay, so all of the other behavior for this rational function should be identical to what the parent function did. It's just going to have a different starting point. Okay, but the same idea shall prevail. Okay, first off, identify your center. Okay, if all of these adjustments and all of these things are going to happen according to where the center is located, then that needs to be your first piece of information. Okay, so look at the equation. Obviously, in the denominator, we have x plus 2. It should say x minus 2, but it does not. So the only possibility is that that 2 is a negative. Okay, and we have the minus 3 hanging on to the end out there. It is supposed to say plus 3, but it does not. So obviously, that 3 must be a negative value. So our center point of our hyperbola is going to be at -2, -3. And there's the plot. Okay. Now what you will want to do is, again, you're going to want to select values in the domain moving each direction away from your center point. And once again, we have radical change in the curve of this graph. So as we move backwards or forwards away from this center point, we will want to pick points that are moving in very small steps at first, and then as we get about a unit away from the center, then we can start moving to whole numbers. So from -2, we would backtrack to like -2 1/4, -2 1/2, -2 3/4, -3, and then expand to larger steps, -4, -5, -6, and so on. Okay, so selecting some values should become kind of a process. Okay, doing the exact same thing each time, just moving away from wherever the center is located. So there are the values that I mentioned. And plugging these in one at a time into your equation is going to yield some values to go along with it. Now, those of you that have a habit of using the calculator to do everything for you, like typing this equation into the chart or into the equation editor and then looking at the table, well, good luck with that, because you're going to be missing a whole lot of points in this thing. You're going to have to learn to plug in values, and it's not a real difficult concept. So let's just kind of get used to it. Anyway, from these ordered pairs, we ought to be able to plot some points, and there they go. We connect the dots, and we have half of our hyperbola. Now we will repeat the process, moving to the right away from the center point. Center point is at -2 in the domain. So we're going to take some small steps moving away from the domain, or moving away from the center point to the right. So we'll go from -2 to -1 3/4, -1 1/2, -1 1/4, and -1. And again, now that we're about a unit away from the center point, we can start moving in some whole steps. So from -1, we can go to 0, to +1, to +2, and so on. Pardon me. Okay, and once again, taking these values and plugging them into the equation one at a time, we will end up with some y values to accompany these x values. There they are. Transferring those ordered pairs to the graph, we end up with these points, and we connect the dots, and there you go. It is not that difficult of a chore. It is, however, a little bit tedious. Okay, let's look at one more together. Hopefully, looking at the equation of this rational function, you should be able to spot pretty much right off the bat that the center point has been moved and the speed of the graph has been changed as well. So we will begin exactly the same way as we have before. Okay, if everything is dependent upon where the center of the graph is at, then we better identify the center. Okay, We can see in the denominator we have x minus 1. That is supposed to be a minus sign in between there, which means that 1 did not bring a sign change of its own, so that must be a positive 1. The constant hanging on to the end back there is a positive 2. That is supposed to be a plus, and it is, which means 2 did not bring a sign change of its own either. So our center is located at positive 1, positive 2, and there is the plot. Now, it's not going to change anything as far as the values that we select, only the starting point. Okay, so in the domain, we are at positive 1. We will want to step in small increments, moving away from positive 1 at first, and then expand to larger steps as we get about a unit away. So from positive 1, we'll backtrack to 3/4, 1/2, 1/4, and 0, and then whole steps to -1, -2, and -3. Plugging these values into the equation one at a time yields these y values. And these values, when plotted, give us those points. And when you connect the dots, there is half of your hyperbola. Now, as you can see, our hyperbola has drifted further away from the center point than the parent function did, and that was because of the whole number 2, or the larger number 2 in the numerator. It's larger than 1. That causes it to push away from the center point and closer to infinity. Okay, these are a little bit harder to predict than some of the other graphs. Okay, but you will learn to see the little similarities that they have. Now, once again, we have the other side of the hyperbola to look at. Our domain is at 1 on the center, so we will move in small increments moving to the right, so like 1 1/4, 1 1/2, 1 3/4, positive 2, and then in whole number steps from 2 to 3 to 4 to 5, and so on. And again, plugging these values into the equation one at a time, we end up with these y values to accompany it. And plotting these values, we end up with those points, and we connect the dot, and we end up with that graph. And again, you can see it's been pushed further away from its center point, and that is because of the constant a becoming larger than 1. Okay, so a lot of things, like we said, the more complicated the graph, the more advanced the graph, the more the plotting method becomes the method of choice. Okay, otherwise, we really don't have any idea where these graphs are supposed to be crossing their various grid lines, and that is a concern. So plotting is kind of the deal. I know a lot of you don't like it, but you're just going to have to get over it. The higher you go in math, the more you are going to see this method. Okay. Well, I appreciate you getting your notes taken care of. I will see you in class.